The first substrate is shown not binding with the active site because the enzyme is specifically shaped for a specific substrate, but now another substrate is binding because it's the substrate that is meant to bind to this enzyme. Shown now is the locking key. The job of this enzyme is to break down substrates. The substrate is now entering and binding to the enzyme at the active site, where it will be specifically made to fit. The enzyme is now breaking down the substrate into two product bipieces. The pieces of substrate that enters the binding site of the enzyme causes it to change shape to push the pieces together. This is called induced fit. You have a substrate that enters the binding site or the active site, so the enzyme is going to put the pieces together so that what leaves is the product. What is being shown now is a non-competitive inhibitor. They halt the production or the breaking down of substrates by attaching to a place that is not on the active site. As you can see, when the substrate tries to enter, it's not able to. What is being shown now is a competitive inhibitor. A competitive inhibitor binds to the active site. This bonding blocks substrates from being produced or broken down. As you can see, the coenzyme is going to help bind the substrate into the active site, and it's going to help break the substrate down. What is being shown now is a cofactor, and this cofactor is going to help make the substrate. And also the cofactor is going to help with the substrate binding to the active site. So this graph represents how there's more substrates than there are enzymes. So the enzymes are constantly breaking and making, and it's at a constant rate since there's so much more substrates than the enzymes. So the blue line on both graphs represents a reaction without an enzyme, and the orange line represents a reaction with the enzyme. Enzymes lower the activation energy, which is the energy required to start a reaction. So since the reaction is an enzyme, it takes a lot less energy for both of them. And then this is the start, this is the end for both of them. And since the starting point is lower on the graph than the end, that means that the energy is being stored. And it is a endocytosis reaction, opposite of this one since the starting point is lower than the end. Exocytosis reaction, and energy is being released. This graph shows how enzymes need a specific temperature to function or else become denatured. This graph shows how enzymes have ideal pH balances that is needed for them to survive and not become denatured. So this graph represents a higher enzyme rate to substrates. So there is a big chemical reaction and then it just goes down after that.